So the second method we would like to talk about in making the carbon nanotube yarns is basically the CVD approach. And so even the carbon nanotubes in the previous method, this method, the forests were made through CVD. And so basically it was, but directly drawn from forests to generate the yarns. In this case, we used a different approach to make carbon nanotube yarns. And so the whole idea behind it was that we have the CVD approach to make the carbon nanotubes, and we get mats of them, and then we scroll mats, we roll them up into individual yarns. And so the idea behind that is very simple. A mat can be a very fragile structure. It can break from ends. But if you roll it up, so if you roll it up like that, now it appears much stronger because there's no edges to break. Whereas when it was like this, open mat, a single small flaw in here can easily lead to the failure of this guy. And so in the process of rolling it up from a mat to a yarn, we also may use an atomizer to spray some liquids on it. This liquid can serve several purposes. One is we can use a very dilute concentration of a polymer and spray it onto the yarn. And when you do that, the solvent evaporates, and this polymer can act like a matrix between carbon nanotubes. Still not 100% wettability, because carbon nanotubes that were touching each other in the matrix, in the mat, will keep touching each other. The polymer will not be able to go in between them because this van der Waals forces between carbon nanotubes is rather strong. So at the end, you will see a structure like this. It has ridges. I tell you what these ridges come from. And if you zoom in, you see individual carbon nanotubes like that. Now, when you look at the cross-section of this material, you see a very peculiar structure. So these ridges that we see here are actually here and here. And you see these are folded structures. These are, when I take my yarn and I roll it up, I see these edges. These are the edges that I'm seeing here. Okay, and so where do they come from? This is a very interesting subject. Where do they come from? When I'm rolling up a mat, I'm twisting it basically, and so this generates some compressive forces and some tensile forces, and this is a very important concept in solid mechanics. If I apply a shear force like that, which is what the twist does. If I look at another plane in this guy, which is 45-degree rotated, in this case, if I calculate the stresses, the principal stresses, I will have these principal stresses. I will have tensile and compressive, normal and basically these are with respect to this direction, normal direction. These are 45-degree angle. If you, any of you who don't have a mechanics background likes to know more about this, please let me know during office hours. I can explain that to you. Now, I'm sorry, but one last thing, this angle is not necessarily 35 degrees. In case of pure shear, it's going to be 35 degrees. But when we're dealing with a mat, it's slightly off. It's about 37 degrees because of some in-plane deformations. So And so we have these ridges. So, and these basically, the ridges have formed when the compressive stresses lead the plane to buckle. That's a very important thing. So these ridges form as a result of buckling. Now, when you look at them or look at these, you can think of them as fibrils that are going like that at an angle theta. So these are like filament yarns that are going at an angle theta, and they contribute a lot to the ductility of this material. So here I'm going to show you a tension test we did in SEM inside a scanning electron microscope. So we stretch the yarn. So the angle goes from initially 23 degrees. It's a special case that we twisted it to get 23-degree angles. And this 23 is a slightly lower than 37 because when we're twisting it, we're also stretching it as well, a little bit. Now, when you apply loading, axial loads, you go from this angle 23 to 16 to 10 degrees, and that's where about this guy fails. So you can think of it as two deformation mechanisms contributing to the ductility of this guy. If I think about one ridge, let's say this guy, that I'm going to plot it here. If these are the two ends of this ridge, and initially this angle is 23 degrees. When the angle goes down, this point, with respect to this point, has moved, by this amount. In addition to that, I can stretch this guy. This guy can get stretched because it's a mat of carbon nanotubes. So basically, and if I draw the stretched version of it, it can go here. So basically, I have two components of a strain. One is this guy, and one is this guy. This is what I call the material strain, and this is what I call the reorientation strain. They both contribute to the ductility. Now, there's an equation in this book that you can read about. So basically, we can decompose the contribution of reorientation and the material deformation based on two parameters, Q0 and Q, which are defined as a function of theta 0 or theta or theta 0. Theta 0 is this, theta is this. And the interesting trend we see is that, as a matter of fact, first of all, we get a huge ductility. We get about 20% ductility, and we get a strength of about 1.4 gigapascal, which is a rather high strength. But also, we realize that this material strain is only half of the total strain. So that reorientation, which happened because of this buckling, indeed contributes to the deformation of the material, because this guy is reoriented and stretched. Okay, both of them contribute to this high strength. So basically, this buckling reduces the stiffness in this direction. So now this guy can easily reorient, or much easier reorient, and then get stretched a little bit as well. Okay. So, and so for instance, now we can use these yarns as strain sensors. And so this is a typical experiment we did. So this is relative change in resistance. So the y-axis we are dealing with is actually delta R over R. And the y-x-axis is a strain. There are two components to the change in resistance. Initially, at low strains, this is up to here about, which is about 2% strain. The behavior of the actuator is linear, and delta R over R is, we can go to about 35% of change in resistance at 2% strain. So that means a gauge factor of 17. Keep in mind 1 plus 2 nu was less than 2, and the rest of it is the piezoresistivity. So these yarns clearly qualify as piezoresistive materials. In addition to that, when you go higher strains, you realize that there is a portion, when I unload it, these points are unloaded, when the material is fully unloaded. You realize that there is a little bit of a strain left in the material. These are plastic strains. And the reason for that is when I stretch them, look here and here, at some point, these two slide over each other. Compare this length with this smaller length. This guy basically is slided. And this sliding is irreversible. It's plastic deformation, which also leads to a permanent change in resistance. So we can use that as a way to also investigate damage in the material if we can define damage as excessive deformations. So the first component, the linear component, piezoresistive effect. The second component related to changes in the overlap length, which results this yellow zone versus this yellow zone, which results in an increased resistance. So I'm going to stop here and continue in the next slide.